And there we go. Another day of fun in the sun. All right, so let's talk about logistics, since that's where I always start. It's always pretty boring. I don't know what's going on with Jonas, if he's back yet or not, so I didn't change that. I don't know, how many of you actually days office hours at all? A couple people stopped in on mine, but there's no more deadlines this week since the deadline for today just passed 48 seconds ago. So hopefully you submitted your design. There seemed to be lots of people who wanted more time to do so. Next week your code is due. No, sorry. Following week your code is due. Next week we have 2 more lectures. You don't have any big deadlines next week. There's just the report. And I am going to add, I haven't added it yet, but I'm going to add the design recipe self-assessment. Remember, I had you do a design recipe at the beginning of class, and I did promise that I'd give that to you before I finish the term. I'm going to do that. So go back and reflect on whether or not you're any better at defining what's important when you design a distributed system than when you started. It's not intended to be like a 3-hour activity, more like a 15, 20-minute kind of activity. I just added this today. There are 247 questions. They are just the assessment questions. They are on a practice quiz on Canvas. I even took the 70-minute. Originally, I set it up like it was going to be a practice exam. Then I was like, screw that. So you don't have to. There's no time limits on it. There's no limit on how many times you take it. I don't think you can actually see the correct answers until you submit it. And it will show you what you got right and what you got wrong. And I'm sure that someone will probably take all of the effort necessary to somehow move all of those questions and their corresponding answers into a sheet of paper. And so I'm not using any of these questions on the final. That was originally my idea. I just imagined that anybody would go through the effort of memorizing 247 questions and their answers. But apparently, somebody wasn't happy with that. So the powers that be said, no, you can't use the questions. I'm not using the questions. That I'm generating new questions. Fun. I'll be doing final prep next Thursday. 1 week from today will be final prep. That'll just be going over what does the final look like, what are the kinds of topics. It's all going to be drawn from readings, the lectures. It's not going to include the last couple of sessions where I'm just talking about things that are more of interest, largely because I don't really want to be pushing you to spend out your time on anything other than your capstone at this stage. And how many people submitted a design on or before 5 p.m. today? A couple people. A couple people are like, I don't care. I wanted my minimum grade so I can get the hell out of this place. Fine too. No problems. Since I had a little bit of time before class, I said, why don't I put together a design scenario? This is the kind of design scenario that I'm planning on using for the final on the 22nd. I'm going to try and use similar scenarios for the true-false multiple choice exam as well. It'll probably be a little bit smaller than this one. This is actually a really good one. So you are tasked with designing a global content delivery network. And the question is, how are you going to approach this problem? Because remember, I have said all along, I think that being able to analyze and design the solutions and reason about them is much more useful as a set of skills than being able to hack together some crappy code for an auto grader. So here was one that I literally just put together before class. I put another one together that I really like and I'm actually going to use, so I'm not going to tell you what it is right now. But this sets the framework of what you'd be asked to consider, right? What is a content distribution network? Anybody know? Right. The problem is that if what you're doing is streaming TikToks from China, it takes too long for you to get them onto your phone. So what actually happens is that TikTok gets cached in some intermediate node that's way closer to you, where closer is entirely based on the latency to get to you. I talked about Cloudflare. Cloudflare's entire business model was, in fact, content distribution. They move content to the edge, close to you, the edge, so that you can get that information on your phone as quickly as possible. One of the big uses of key value stores are, in fact, in CDNs. So this is a good question for this class because I have at least mentioned very briefly once or twice every 2 minutes key value stores. But this adds some extra considerations on top of that. This is more of a real-world kind of consideration. So I've talked about all these pieces and whatnot. Part of the goal of the capstone and part of the goal of what I'm trying to get you to do here now is to bridge that gap, is to say, okay, I've got this set of tools now. How am I going to apply to this problem? I don't actually care how you solve it. What I care about is the process by which you go through thinking about it. It's your thinking that I want to see. How do you think about these problems? How do you break them down? And since it didn't fit on one slide, I put the requirements and constraints. Plan to support at least 100,000 content creators uploading high-definition video and rich media assets. Small potatoes kind of stuff, right? This isn't YouTube scale or even TikTok scale. It's pretty big. But, you know, this isn't going to be anything anyone's going to build for their capstone project either. This is much more ambitious than what you would do in a capstone project scenario. You need to handle at least 50 million active users distributed globally. So it's that global distribution that justifies the use of a content distribution network. Latency between content origination and display should be less than 250 milliseconds, because above 250 milliseconds is where people can start to see it. That's roughly the edge of human perception, is about 1/4 of a second. Video should adaptive stream with no buffering at qualities up to 4K resolution. Boy, now we're Netflix. Anybody know how Netflix actually deals with video? Netflix constantly measures the latency and the jitter and the bandwidth on your network connection and will change the quality of what it's delivering, because what's more important is that it delivers things on time than it delivers them with high quality. Here's an interesting thing that I learned years and years ago. When we are delivering audio and video, the thing that we are most sensitive to are audio dropouts. You can degrade the video quite a lot, but you do not want to misdeliver audio. Very interesting. It has to do with the way that humans process information. And this is an interesting problem because frequently what we end up doing is trying to deliver audio and video as separate channels, but at the same time. They're called isochronous services. There's lots of fun problems here. Are you going to explore all of these in a, I don't know, 2.5 hour period? No, definitely not. I don't expect you to. But what I do expect you to do is to start thinking about the problem and say, this is how I would approach that problem. You've already gone, so I'll go there. About 1,000 to 1. I mean, it's huge. Audio, we are really good at compressing video, but we're really good at compressing audio as well. And audio, you can actually clip. You can do lossy audio. You can clip at about 3,000 hertz, and most people cannot really tell the difference. Like when you use a standard telephone line, which doesn't really exist anymore. You go visit your 92-year-old aunt who still has a party line. Do any of you know what a party line is? So it used to be that telephone lines ran on copper wire. Some of them still do, like the last little bit. And it was so expensive that you had to share a single phone line between households. When I was a kid, we actually had a party line. You had to pick up the phone and see if somebody was using it. If they were, you had to hang up. It's still supported today. Anybody who has a party line still has a party line, but they don't install new ones. They haven't installed new ones in like 2 decades or something. But it has to be supported because there's still your 92-year-old maiden aunt there in nowhere whose neighbor shares a line with them. It's pretty crazy. Those clip. Telephone lines actually clip at 3,000 hertz. It's very, very low bandwidth, very small, and you can do an uncompressed telephone line requires 56 kb. 8 kb of overhead, so it's 64 really, but it's 56 kb. And in fact, people got really good at compressing that down. You can get that in under 14K. So it's not a very high bandwidth connection, and it's good enough for you to have an audio communications. That's why you can use voice on your phone over data, and it still works really well. It doesn't take very much data to do it. So adaptive streaming in videos is what Netflix does. And then content and infrastructure should survive at least one regional outage with no visible disruption. So of course, there we go. There's the interesting hook that you're probably going to say, I'm going to build that. Well, gosh, what have we talked about in this class that could possibly do that? I know. I'll put them in a station wagon and drive them to the other side of the world. Did you actually have a question earlier? Well, actually, they use quality of service mechanisms for doing that, and it depends. There's no single solution to that either. But yes, they end up having some sort of protocol that allows them to prioritize certain streams over other streams. And a long time ago, I worked for a company that built asynchronous transfer mode networking equipment. You've probably never heard of ATM equipment, but ATM equipment, not the banking machine, networking machine. ATM equipment was actually designed to do circuit switching, which is a telephone connection, over a packet switch network. They used a fixed size packet of 48 bytes. And the switches themselves were built to be blazingly fast because at 48 bytes, you could build hardware that would start retransmitting the packet before it had finished arriving, which is a really cool thing. They're literally called cut-through. So you get enough of the data in on the inbound connection, and you know where it's going to go on the outbound connection. You literally start sending it down out the outbound connection. And it had guaranteed bit rates. So you could do constant bitrate services. It had variable bit rates. So the difference there is that if you have a constant bit rate, you're paying for that bandwidth whether you are using it or not. If you have a variable bit rate service, you're paying for some average amount of delivery, but you might actually get squeezed sometimes. But power companies do the same thing. And we'll give you a cheap rate on the power when we got plenty of it, and we're going to charge you an arm and a leg when it's scarce. Ask the people in Texas who got hit by that. It works really well, except when it doesn't. So that's the kind of design scenario that I'll be talking about, and I'll be using similar scenarios in the finals. I had to reach around for a failure, so I went to the Microsoft Azure website and dug up a failure from September. And what's cool about this is I actually have a video of it. I've got a link on one of the slides to the video. You can actually go watch them explaining this because it impacted customers. And so they had a customer-facing presentation of their analysis of the failure. So it was kind of cool in that what happened was some scaling units. Now, scaling units are how you deliver more services on demand. So in essence, they become load balancers. That's a scaling unit, right? Is it, oh, we got a burst of traffic, so we need to start routing this out so we can continue to maintain it. And this is a big thing. This dynamic scalability is a huge thing in distributed systems because Slashdot still around? Slashdot used to be this web service like Y Combinator or something like that, where there would end up being news stories. And it would basically promote somebody's website, for instance, done something notable or interesting, and suddenly they get slammed. It's like getting on the front page of Reddit would do that to you, same sort of thing. So suddenly, you've been picked up because of something that you did or said or somebody said or did about you that causes your website to get massively hammered. And rather than go down, you bought scaling services. What happens is suddenly Microsoft throws huge amounts of resources in front of that to provide your services. And so your website continues to work. But then Black Friday is over and you're special on, I don't know, mouse widgets is, those are the things you feed your mice. You ran out. There's nothing else to buy. Nobody's interested. It's not Black Friday anymore. And so your scaling goes back down. And so the resources you're using go back down. So that's what their scale units are about. They lost power. Okay, power goes away. Happens all the time. Yes. Depends on the size of the burst, but generally you expect responsiveness within 30 to 60 seconds. The larger the burst, the more resources you have to bring online, the longer it takes. But generally what will happen is it'll get a little congested for a bit, and then it'll settle back down. I mean, if everybody goes and hits it all at once, then you probably have a denial of service attack going on, which is a completely different problem, which we also would have to address. But that wasn't the issue here. The issue here was just that the power went out. Oh, darn. Well, wait a minute. Don't they have UPSs for these kinds of things? Why would they actually lose all this hardware because the power went out? Well, okay, so at any rate, the power went out, their scale units rebooted, and then a subset of them, for some reason, failed to come back online. It's like you plug your computer crashes and it reboots, except it doesn't reboot. Had that happen to me over the summer. Happens. It's frustrating. What is going on? Why did it do this? Some customers using proxy mode connections may have experienced impact due to one connectivity gateway not being configured with zone resilience. Oops. So it's just this like little configuration issue that one thing didn't have replicated services. So the people who are behind that non-replicated service, sorry, you're out of luck. This is not a good thing for a distributed systems company, right? This is not what you want to be telling your customers. It had some interesting impacts, where SQL databases with auto failover groups started failing to different regions and required 8 hours of downtime to complete their failover to a different region. That's not exactly what I would call a seamless failover. It failed over. It did take 8 hours. It failed over, but if that was your website and this was your widget sale on Black Friday, you'd be really unhappy. Fortunately, that was September 16th, which I think was just this unremarkable date. It wasn't Black Friday. Tomorrow. Why is it the rest of the world gets inflicted with a curse from the US? And the best part, the root cause of the actual power failure was this incident was initially triggered by a UPS rectifier failure on a primary UPS. So get this, they did have a UPS, the UPS failed. The power went out, the UPS failed, so the backup failed. The power stopped working, and have it? Yeah, and then they've got all these interesting notes about how there was some sort of weird BIOS problem, and some of the VMs didn't restart, and you get digging into this, and you're like going, wow, this is a cascading failure situation. And that's what ends up happening in almost all of these cases. These guys know how to hit the primary failures and deal with the easy stuff when one thing goes wrong. And we've been talking about some of those basic ideas, network partition and power fail and nodes dying and whatnot. But this is like, well, and this has been a theme in all of our failures, right? It really has been. These people who are sophisticated and know how to do this will build these redundant systems. And sometimes those redundant systems don't work right. And sometimes the redundant systems don't work the way that we wanted them to, like the 8-hour failover. So what's cool to me about this is it's not a single failure. It's like a dozen failures all wrapped up in a nice little basket. And the wheels didn't fall off. It's not like everything fell apart, not like the Eastern Australia one where it basically melted an entire data center. But it was still pretty bad. So, BIOS issues? BIOS? How could that possibly be involved in a distributed systems failure? Well, because distributed systems are made up of nodes, and nodes are running on computers, and computers use BIOS in order to reboot. And then a monitoring deficiency. So not only did things go wrong, but the tools that we build in order for us to figure out what went wrong and how to fix it didn't work right either. Like I said, it's a whole basket of lots of different things that went wrong. So from an incident report, this is a really cool incident report. It was lots of things came unglued. And there's a video there. The link is there. You can get it from the slides, which are posted. Today we're going to talk about data center services, which I thought that was a great failure because this is exactly what data centers do. They provide these kinds of services to people, and our concern is how do we keep those services flowing to our customers even when things go bad? Yes. There are actually specialized people who design physical data centers that, because there are crazy stories of, I got one story from Andy about this a couple of years back where they were talking about how they designed a data center and they put power generators in them, right? So they put backup generators in the data center. In this particular data center, they put the backup generator above the computers. Well, they use fuels that will produce water. And so this generator sat in a pan, literally like a bathtub kind of thing or a shower pan, so that if the water started flowing, it would go into the pan and then out a pipe. Someone screwed up on the sizing of the pipe. It was too small. So the amount of water that was being produced exceeded the draining rate of the pipe. They found this out when they ran a test. They were testing the backup generator. The backup generator started producing water. The water started flowing out through the pipe, but not fast enough to clear the water, and eventually it overflowed onto the computers below it. And the computer science department has extensive experience in aquatic computing, and I assure you that it is not a pleasant one. In fact, the same room flooded last year, shortly after about $2 million worth of new hardware had been installed. That was Margot's. Yeah, like 60 days or less after it had been installed, and it destroyed everything. Destroyed all the computer equipment. It had to be replaced. I suspect that UBC self-insures, but that might have been a large enough claim that they would claim it against reinsurance. You may not know much. These are the things you learn as you like develop software for people. Insurance companies tend to fall into different categories, and one of the specialized kinds of insurance are what are called reinsurance. So they only insure things above a certain threshold. Like your main insurance carrier will cover you up to $1 million, but you have a $5 million policy. So a reinsurer will cover anything above $1 million to $5 million. And I know a lot about this because I do consulting work in the litigation field, and insurance companies pay for litigation. They pay for fat guys like me come in and and explain technology to people in the jury who are falling asleep. I've been there. I've done that. They didn't fall asleep when I was talking, though. They were laughing. I'm sure you find that hard to believe. Pretty fun. You get to all sorts of useless things like this you learn, no matter what you work on. And it changes your perspective of the world. All right, so let's talk about data center trends and services, high-speed RDMA, resource heterogeneity, resource disaggregation, resource management, and orchestration. These are kind of more cutting-edge sorts of things in how we design and build data centers. Some of this is still somewhat researchy, but I have to tell you that a fair amount of the research that comes out of these areas is in fact coming directly from the cloud folks themselves. So you will see papers from Azure, you will see papers from Google, you will see papers from, who's that other company? Amazon, right. So, you know, the people in Brazil. They all publish papers, and they all talk about these things. Now, their papers are interesting because they usually are patting themselves on the back about what an incredibly good job they did, and they provide you with just enough detail that you can sort of vaguely get an idea of what they accomplished, but they don't want to tell you how to actually do it because you might go and compete with them. Lots of interesting things that drive this business. One of the most of them is, have you ever heard of Moore's Law? I actually read Moore's original 1965 article. It's not even a paper. It was an article. It was something he said to the tech press of the time. And what he said was the rate at which the number of transistors on a solid-state device are increasing is about 2x every 2 years, I think it was. And it went down to about 18 months. But it's actually hit a wall. It hit a wall a while ago. And we use different techniques now for scale up. But Moore's Law was really this observation that, hey, we can keep making things skinnier and smaller and faster and more capable. And that was 1965 when he said that. And we're still seeing continuous growth in this area. It's not necessarily at the same speed as it was before, and we're having to use other techniques, but it hasn't really stopped. I mean, we've got the big thing for Black Friday sales now is to buy 20 terabyte hard drives. 20 terabytes. There was a paper that someone wrote a number of years ago where they said that they could keep track of absolutely everything they did on their computer with about a terabyte of space. And literally, they meant everything. You could go back to any point in time and reconstruct any state that computer was in over the previous year. That's a terabyte. I like that number because that's actually something you go, wow. That sounds like a lot of information. But yes. So 20 terabytes. You can keep track of the next 20 years worth of stuff in there. So we see this all over the place. In fact, I would say that CPU growth has decreased, but storage growth has increased. The size of storage devices continues to grow rapidly. Networks continue to get faster. CPUs, not so much. It's really expensive to build a very high-frequency CPU, and there's only a handful of people who actually do it. Mostly because it's really expensive. It generates lots of heat, blah, blah, blah. How many of you have a GPU? What GPUs do you have? See, he is a gamer. He took the world's best card ever and is sticking with it. Actually, at the time, it was really, it's been really kick-ass. It is a really good GPU. Right. And anybody else? You know, you got a Radeon 560 or something? There you go. All right. And I can show off because I got, you know, a 4090 still. With a water block on it. And why do I have a water block on it? Because those are all high-frequency cards. All these new graphics cards are very high-frequency, and as a result, they generate lots of heat. And heat is the enemy of semiconductors, the enemy of data centers too, so we have to keep track of that. So part of what ends up happening is that we end up making things that are faster, like GPUs, faster and more capable, but we separate them out. So we build a really fast GPU, but that's separated from the CPU. You don't see a lot of combined GPU-CPUs, except when you go to SOC. When you do systems on a chip, like things that go into your phone, often these things are all integrated into the same physical package. So it's kind of an interesting difference in scale. In data centers, on servers, we tend to do more and more specialization. When we look at small devices, we tend to do exactly the opposite, which is we do more common packaging. And then I'll screw with your head and tell you that, in fact, we're using SOC chips in data centers now, too. It's all over the board. This idea of disaggregating the functionality is one that's been going on for a while. There's a lot of research that continues to go on here. We have added new kinds of memory. One of the people I work with over in ECE, Sasha Fedorova, has been doing in-memory compute research. So that's the idea that what you really want to do is you want to stick your CPU in the middle of a blob of memory so that it's very close and very fast to communicate to that memory. You can do certain kinds of operations that's applicable to certain classes of problems. I did a bunch of research in persistent memory. Intel and Micron had a product. Intel called their product Optane. And it was actually a DRAM compatible memory, where you literally could take these memory DIMMs and plug them into a computer that knew how to talk to them, and you talk to it like it was DRAM. It was slower than DRAM, but it was still interesting, and it was more dense. It was 9 times as dense as DRAM, and that meant it was cheaper. And so we see people playing with all of these different technologies. Intel's gotten out of the persistent memory game, but there are still a number of people who are playing in it, and I think it's more a matter of time before we see it happen again. I thought that Intel went the wrong direction. That's from my observation. It was slower, but it was much more dense, and it had much lower power footprint, so it was cooler to run it as well. And they put it on these really high-end, kick-ass machines with lots of cores. You know, like 48 cores. I was working on these experimental 48 cores, and I'm like going, but the memory's slow. I can't share memory, so why are you doing this? What I want exactly the opposite. I want the cheapest, slowest freaking CPU you can give me, a lot of memory, because I want to collect a lot of data, not because I want to process a lot of data at high speeds. It doesn't matter. It'll come back, or not. Disaggregation is really interesting in that what it does, it says, let's build farms of just memory. Let's build farms of just storage. Let's build farms of just GPUs. And this is one of the things we do in data centers. So there's this constant stream of new technologies coming out. We've got NVIDIA and Mellanox coming out with high-speed interconnects. Anybody ever heard of InfiniBand, CXL? Fiber channel. Fiber channel is old. It's one of the earlier high-speed interconnects. InfiniBand has been around for quite a while now too, and that's what most of the large clusters of computers use is InfiniBand. But CXL is now emerging, and that's yet another cutting-edge technology for attaching lots of storage and having different computers communicate with each other, because when you look at them, it looks an awful lot like any other distributed system. These interconnects are networks. These days, even your basic computer, I remember when this switchover happened, is PCs, cheap-ass PCs, moved away from having a simple interrupt to having what they call message passing interrupts. And when you start moving to a message passing interrupt model, what you're getting are messages from the hardware saying something interesting happened, rather than raising your hand and waiting to be called on. Because that's what the original hardware interrupts did. You asserted a line on a bus, and the CPU would notice and say, oh, what did you want? But now instead you said, here's what I want, and you put it in a queue, and it gets processed. So it's much more like a network. So Micron and Intel did the persistent memories. We have these interesting virtualization techniques like Docker and Kubernetes use. Kubernetes being a orchestration tool, Docker being an isolation tool. So the idea behind containers, behind Docker, was it's cheaper than virtual machines. Maybe, maybe not. I saw a paper a couple of years ago at SOSP, 19 Dresden. There's a wonderful place to visit. Very industrial former East German town. It was actually fun. And it was very interesting because it said, my virtual machines are faster and lighter than your containers. And so it was the idea that you don't have to make virtual machines be big, monolithic, heavyweight things. There's always people pushing at all the edges here. And we see some of those things end up in the data center because what do the data center people care about? They care about scale, they care about performance, they care about cost. Google and NVIDIA have been really good about building specialized accelerators. Google has these TPUs. They're the ones who came up with the whole idea of having these tensor processing units. How many mathematicians in here? He begrudgingly raises his hand going, do you know what a tensor is? Yeah, fine, okay, great. Exactly. You know, one of those funky matrix thingies. They're just a very efficient way of expressing certain kinds of operations. And they use them a lot in physics. Physicists love tensors. Well, it turns out that tensors are also used for machine learning. We're doing big matrix operations. And that's what a TPU does. It does highly efficient matrix operations against this particular kind of mathematical structure. And we're building hardware to do it. We use GPUs because, yes, GPUs can be used to run games really well. But that's not the real reason that you go and get a GPU, right? Right. That's what you always tell yourself when you're rationalizing the purchase. I need this so I can run TensorFlow. Right? PyTorch, TensorFlow, got to get all that machine learning stuff going on it. That's it, yeah. I haven't run a single PyTorch or TensorFlow on this GPU yet, but I will. I'm looking at programming my own large language model since it would appear that, you know, the people who are purveying these things aren't very stable. I could have used that as the failure of the day. Except it's not over yet. I'm going to wait. So there's this interesting idea called remote direct memory access. And RDMA is this idea, and I have mentioned it before, but it's really actually heavily used in data centers now. The idea behind RDMA is don't involve the CPU at all. Use the NIC card to stuff something in memory on another computer. Huh. Okay. So this is just a big distributed shared memory model. Now, there is a trust relationship here, obviously, because if you start letting me shove things into your memory, then you probably are going to have to trust me to do that correctly. Maybe you're going to corral the piece of memory that I'm allowed to shove things into, which would be perfectly reasonable. But you can understand that this makes sense in the data center because the data center people trust their own hardware. But there are interesting security implications for some of these things as well. This isn't a security class. I really haven't touched much on security. But security becomes a huge issue in any multi-tenancy environment. Because your stuff and your stuff are running on the same machines, and you can steal from him. Or he can steal from you. Or he could be devious. This is the spy versus spy thing, right? And then he could be feeding you false information. Or real information, kind of like that that Canadian dude who just got convicted of passing secrets to the Chinese. It's like running a spy agency. Pretty bad. If you're going to do those kinds of things, don't put them on your own personal computer in a subdirectory called Batman. And don't make notes in your personal calendar explaining how you're trying to get people this information wise. The benefit of remote direct memory access is it bypasses the CPU. It is very high bandwidth. It has lower latency because you don't have any CPU overhead. There's nobody on the other computer has to do anything with it other than the hardware itself. It's all hardware mediated. It's much more expensive though. This is specialized hardware. This is not commodity hardware. It actually is commoditizing to some extent. Like everything in our business, once somebody comes up with one of these clever ideas, they build this really expensive hardware, they get the non-recoverable engineering cost recouped, and then they start pushing it into lower-end devices. So now you can go buy yourself a $5,000 card that handles all of this instead of a $105,000 card. RDMA is an ancient idea. It came from the 1990s. That's like, prehistory. There were some models for this in the early 2000s. InfiniBand, which was developed by Mellanox, I mentioned, was a mechanism for doing high-speed intercomputer data transfers. A lot of it was used for clusters. And that's, in fact, exactly what it says. Approximately 50% of top 500 machines are using InfiniBand. And that's because that's how you build supercomputers these days, is you strap together a whole bunch of computers, give them a very high, very expensive shared network. You can move a ton of data really fast. They use crossbar switches. Crossbar switches are extremely expensive to build. They're very blindingly fast because they don't aggregate the traffic. They literally have connections between every point in the network, or a large percentage of them. This is now converged into RDMA over converged Ethernet, which is a standard. So this is how network cards implement these RDMA protocols. And there's now a wide area network protocol. So, let's forget about the fact that we did this originally because we wanted that low latency. And now we'll just do it over the internet. Good question for the final. So you've been called upon to design an iWarp network with the new Lunar Data Center. And so RDMA can, in fact, be CPU aware, which is still faster, but not as advantageous as having one-sided RDMA. In one-sided RDMA, we don't actually tell the other CPU what we've done. Because this CPU over here, we still have to have a control layer. So the CPU on the left is controlling the data transfer, but the CPU on the right doesn't directly know. It doesn't have any direct involvement. Well, there is a little bit of a problem there because that means that the CPU on the right might have stale caches now. So we do cache injection because we say, well, you've got a cached copy of that data. So here's some data in your cache. Or if it's not in your cache, it is now, and you're going to be able to process it faster. So it's literally like preceding the cache from the other side of the connection so that when you have to reason about what's in that packet, it's already in the cache. It's already faster. This is all about performance. RDMA is completely a performance play. It is all about how fast can I move these bits around. Yes? Yes. Well, okay, the CPU on the right has to be built to allow cache injection from the RDMA layer. Yes. You just can't take your commodity CPU and have it do that. We have RPC over RDMA because, of course, how else are we going to package things up? This is a network, and once we have a network, we need to have a presentation layer because we've got to serialize the data correctly. So here we have this really cool way of communicating over RDMA using RPC. But very optimized. It's still really, really fast. The primary benefit is it doesn't have to involve the CPU at all. Or if it does involve the CPU, it can keep that involvement to a minimum because most of the work is still being done by the NIC card. So even when you're using the CPU to initiate the transfers, the NIC card is the one that handles all of the iteration over that because, hey, let's transfer a terabyte of data from this machine to that machine. And it's going to take a while. But the CPU won't know, and it can go do something else. Question? Yes, they are two physically different machines. Okay, these are NIC cards, so they are actually running at the Ethernet layer. So it is running either at, so it's running above the PHY layer, it's running at the data link layer, or if you go to iWarp, then it's clearly running at the internet layer to use the obsolete system interconnect model. A term I first heard from David Sheraton, who's a UBC grad. I've not mentioned that. So the benefit of using RPC over RDMA is that, in fact, like I said, it's really fast. And we've got a nice little chart here. This is from a 2016 paper, so it's like within your lifetime. So this is fairly recent work. And although that's now 7 years ago. Time go. And you'll notice that one of the big benefits to it is that it actually provided uniform performance, which is a huge win in data centers where one of your primary concerns is tail latency. Persistent memory, cool stuff. It was a lot of fun to play with. I got a paper out of it. Tortures of the damn to get that paper out of it, but I got a paper out of it. And it was very interesting to work with. It required rethinking, at least for me, required rethinking the way that you wanted to use this kind of memory. In DRAM, some of you probably remember in 313 where you had paging. Because we don't have enough DRAM, so what we'll do is we'll just simply use some disk space to simulate DRAM, because disk is almost as fast as memory, right? Right? Yeah, of course, it is. Absolutely. Except that now I give you this persistent memory, and I'm going to give you 6 terabytes of it. I kid you not, I was on a machine with 6 terabytes of persistent memory. And so one time I just did the calculation on that. I said, it's going to take like 6 minutes for me to swap this out to a disk. The fastest SSD I could get at the time, an NVMe drive. Maximum theoretical bandwidth. It was still like 6 minutes to switch it out and switch something else in. I'm like, this idea of paging large data sets in and out is stupid. No one's ever going to do it. That's a ridiculous model. But if that's a ridiculous model, why are we paging? And that was the point of the paper. The paper pointed out that we're spending so much time slicing and dicing things up into 4K chunks that it dominates, literally the page fault cost dominated the slowness of the memory. So the memory was slower than DRAM, but the cost of faulting multiple pages in a 4-level page table was so high that it dwarfed the evaluation. And so when we went to much larger pages, like you go to 1 gigabyte pages, the Intel CPUs only give you 4 TLB entries, but it was still way faster than using 4K. Because you got like 1,000 of 4K TLB entries, but the moment you blew through those, it was all over. Because to walk the page table requires up to 4 memory accesses. And even if you're using DRAM for your pages, that's about 600 nanoseconds. And the access time to the persistent memory was about 200. That's why I said it dominated. It's a cool observation. So we can do RPC with RDMA over persistent memory. This is another way to spin these things. It's kind of dead at the moment since no Optane memory. There's still people writing papers about it, though. You know, researchers don't stop just because the hardware dies, because the ideas and the ways we could use this stuff, if somebody else can make it commercially available, are still interesting. In the very first paper that was done on persistent memory, I had read like 4 times until I finally realized they finished in simulation. Because they talked about how they built hardware. They used flash memory, built hardware, put it on a memory bus. It didn't work well enough, so they actually finished it with a simulator. It was like, I'd never picked up on that initially, but the idea was really cool. It's like, why would you separate your DRAM from your storage if the storage is really big and just as fast? And the answer is you wouldn't. You're going to keep seeing those kinds of things. Disaggregation is a big thing these days in data centers. The idea is that what you do is you build, we got these racks. Remember I talked about the racks, and you've got these racks, and what you do is you put a big chunk of memory, and you put a big chunk of CPU, and you put a big chunk of GPUs, and you put a big chunk of storage. And all of these things are talking to each other over a high-speed interconnect, over InfiniBand, over CXL, over essentially a really fast network. How does that work? Well, that actually means that your CPU has to run across this interconnect to talk to its memory, because the memory is actually in a different box. But I look at that and I say, how is that really different? And I remember the first time I saw this stuff, I said, gosh, this looks very much like the way they used to build computers in the 80s. Because everything was discrete and broken out and communicated indirectly through these channels, and then we started putting them together. And then, of course, we go back the other direction. And you'll see this a lot in systems. I've seen it a lot. We'll probably see it as well. We kind of swing back and forth and go, because there's no one correct answer, there's no one golden solution to every problem we have, we tend to oscillate between the solutions, convincing ourselves there must be something better than what we have now, so we'll try something different. Yes? It actually allows us to build very large copies of them, very large instances of them. And that economy of scale does buy us, let's call it bang for the buck. We get more for our dollars when we can aggregate a large chunk of specialized hardware to do a particular task. But it definitely oscillates back and forth because there are costs associated with that. There's more complexity. And that's why this is still a research topic. It's not, we do see this in data centers. Data centers have moved to a disaggregated model for some things, but not everything. There's still tons and tons of discrete servers hanging in racks in data centers. But there are also cases where they really do build, like GPUs are clearly a case where they farm out the GPU separately. When you start doing large machine language models on GPUs, the GPUs themselves are where the bulk of the work is done, and mostly what you need are high-speed interconnects in order to move data, get the GPUs to process it. That's where things like RDMA start to become really interesting, because in essence, you don't really want the CPU to have to fetch the data. You just simply want the GPU to give it back to the NIC card. The NIC card can stick it into the memory of the CPU that asked for the work to be done in the first place. So I think that's a big part of what ends up happening, is that disaggregation allows us to have independence from the CPU. The CPUs become a bit of a bottleneck. Part of that is because of the whole Moore's Law issue. This general purpose CPUs just really aren't getting faster. What we're doing is we're building more cores on them, getting parallelism, but we're not making the actual cores themselves run faster. The people I know that make the fastest CPUs in IBM. Yeah, I just double take there. Yeah, so IBM's mainframes, which is still a very viable business and they still sell them, actually run very high frequency CPUs. Like things in the 8 gigahertz kind of range, 6 to 8 gigahertz. Because if you're spending a couple $1,000,000 on a mainframe, you don't care that you have to actually have water cooling in it. IBM's been doing water cooling since before I was born, and that was a long time ago. So another reason is flexibility. So one of the benefits of having disaggregation is that it's easier for you to scale things. You just add another blob of memory, and suddenly you got more memory. If you need more CPU, you just add a blob of CPU. If you need more GPUs, you add a blob of GPUs. Whereas when you build it into a single package, you're kind of locked into that package. Having said that, I already mentioned that we also see SOC showing up in data centers, systems on chip. But SOCs make sense for running things like your web servers because you don't really need that level of flexibility. Database servers, on the other hand, you probably are going to be running them in disaggregated situations because you need to add more storage. You need to add more TPUs. You need to be able to run specific workloads. There's a large number of papers on using FPGAs, custom FPGAs in data centers. Do really cool sorts of things. FPGAs are fun, but they're not something that, so they're programmable, yes. You can change what they do, but you don't change what they do very often because it's an expensive process to change them. But they can be custom built to handle specific tasks or jobs. So maybe you have a job that's going to take a week to run. That would perfectly fit into an FPGA model because the cost overhead of reprogramming your FPGAs, which might be 20 minutes, is dominated by the time that you're going to use that custom programming in the FPGA. Anybody ever worked with an FPGA? Yeah, I've known people too. There's not a lot of them. It's a very specialized area, and they get almost as much money as you do in distributed systems. Oh yeah. So he's not getting paid that well. My friend at Microsoft lives down the street. And that was just one of his big things. But, you know, Microsoft paid him a lot of money to come there, too. Exactly. Exactly. You know? It's like, cool. But yeah, 230K is a lot of money. How old is he? At 23, 230K sounds like a lot of money. Wait until he's 33. And then he's going to be like, I'm only making $1.2 million. Plus options. Already used. Microsoft doesn't do options. I think the first offer I got from Microsoft was 1,600 options. Turned that down. Resource disaggregation, things like networking are really big here because we were talking about scaling and scale units. And what do we need? We need the ability to be able to plug a device in that can scale up for us. So we have these resource management units. Well, that's a very specialized task. That's all networking. You need a little bit of memory. You need a lot of high-speed network ports. One of my colleagues in the Systopia group has been working with Tofino switches for a while. Tofino was this company that built these really, really cool, programmable, super fast switches. And Intel bought them. And one of the things you will learn as you go through in the tech industry is that when large companies buy small companies, usually what they bought them for ends up getting destroyed. I've watched this happen over and over again. It's really kind of amazing. Well, what the hell? We'll go spend $500 million to buy this company and then shut them down. Because it's cheap. That's why $230,000 doesn't sound, does it? Right, so networking. This was presented at OSDI 2020, so we are definitely, I actually saw this talk too. It was about building an operating system for disaggregated hardware. And so, of course, we start with a traditional view, and then we start moving pieces of it out. We move the DRAM out. Use some sort of specialized network. The MMU still sits inside of the CPU, but now it's talking to the DRAM that's across the network. Well, it turns out that's not a huge change because DRAM is already going through this external mechanism. So putting your memory on CXL, which is now the big rage in space, CXL didn't exist in 2020. Okay, doesn't really change things that much. So, but maybe we get a little bit of flexibility there. You could replicate this. You can run a Paxos protocol over this if you want. Well, What happens if we actually move the MMU, the memory management unit, and the translation look-aside buffer, i.e. the virtual physical translation cache, we can move that to that disaggregated memory. Well, this starts to get interesting. Previous picture was like, not that different. Now, see, now that means that the virtual memory is exposed at the DRAM level, not at the CPU level. We moved the MMU off of the CPU, which is funny because MMUs used to be separated from the CPU. And it was about 20 years ago that we smooshed them together. Here we are tearing them apart. So the point of this presentation was this changes the way that we build our operating system, because now our operating systems are now programming this disaggregated version of memory rather than the version that was just all in one package. How does that change the way we design things? How does that change the way we think about things? It is really cool because this is now the logical step. We move the virtual memory over here. Well, when we start building clusters of these things, because remember, one of the reasons we're moving this off of the same machine and the same platform is we can share it. We can actually have a distributed shared memory system now with multiple computers where the memory is actually on the other side of the network and the virtual address space is the same across those nodes. It doesn't actually have to be identical, but at least some portion of it overlaps. That becomes kind of interesting because now we moved all the memory over here and we're sharing it across a bunch of different computers. So what can we do with that? Remember, one of the things that becomes challenging when you do things like replication is what is the propagation delay? Well, this is going to lower your propagation because everybody's using the same memory. It's like putting a big chunk of memory in your network. Sort of plays with your head a little bit, doesn't it? Isn't that so cool? You could do that. In fact, I would argue that cache coherency protocols are a form of consensus anyway, right? It's just, it has strong it has eventual consistency guarantees most of the time, except when it's strong. I did draw that parallel before when I was talking about consistency. And I see a lot of similarity between the consistency models that we end up in systems and distributed systems. That's why I say the defining line between what is a system and what is a distributed system isn't always as clear-cut as we'd like to pretend it is, especially when we get into these data centers. As much as we'd like to pretend that networks are just as fast as a local memory bus, they aren't. They run about 25 to 50% of the bandwidth capacity, but we have 800 gigabit per second Ethernet, and that means that, of course, somebody's working on 1.6 terabyte Ethernet, terabit. Notice those are gigabits. That's a little b, not a big B. So that's 100 gigabytes, which is still pretty fast. Much higher latency. We are improving slowly, but we can't beat that speed of light thing. But what we can do is we can start using a light instead of using electricity over copper wire, because that's about 50% faster. And that's definitely something I've seen. There's a number of papers recently, like within the last year, that I've seen published about moving to optical computing. And so that helps mitigate some of it. So this is very common in distributed systems as well. We solve one problem and create another one, which then requires that we fix that problem, which then, of course, creates another one. And this is a really important skill to learn as a distributed systems developer because it provides you with job security. No matter how fast you make it, you've now made something else the slow part of the system, and you're going to have to go fix that as well. There is always a bottleneck, always. So what else can we do here? can make the cache in the CPU bigger because we're not using all of that real estate now for an MMU and for a TLB and whatnot. And the TLB memory is expensive. They use the same memory for TLBs that they use for registers in the CPU itself. It's the same as the level 1 cache. There's this SRAM memory, which is a really expensive memory, and that's what we use. I'm playing fast and loose there because Intel does like 2-level TLBs, really fast memory, and there's the not quite so fast memory they use for it. But it's still way faster than DRAM. So now we've got more space. So now we can actually add more cache. So that will help mitigate some of that overhead as well. And we're going to see that complex trade-offs are going on here, where now, yeah, okay, I've got this more latency when I go to DRAM, but frankly, DRAM is already slower than my cache anyway. Does anybody recall? I have mentioned it once, but you probably don't remember. What is the speed, typical speed for a modern CPU when I'm accessing the L1 cache? Not quite that fast, but it is 500. What is the cost of accessing DRAM? Well, that was after multiple page faults. So typically it runs between 60 and 120 nanoseconds these days. But still, 500 picoseconds to 100 nanoseconds is in fact a lot. 200 times. 200x. So it's 2 orders of magnitude. So there's already a huge mismatch in the performance of the cache. So making the cache bigger can be a real win. But it all depends on the locality of the working set. How much data am I actually using? It turns out that locality in CPUs is really good. CPUs are extraordinarily good at like watching in advance and prefetching things and predicting what you're going to do. And I love CPUs. CPUs are just amazing little boxes where you start out and you just assume that everything in distributed systems. Right? Well, I just need to execute some instructions, and then I need to load something from memory. So I just wait until I get that thing from memory, and then I need to make a decision based on the thing from memory. So I wait until I get it, and I make the decision, and then I move. And then somebody says, "Why are you doing? You're waiting 120 nanoseconds to fetch that thing from memory so you can make the decision. Why didn't you just use that 120 nanoseconds to go down both branches?" What? Yeah, so part of the CPU goes down this branch, and part of the CPU goes down that branch, and then when you actually get the result, you just kill the one that was wrong. Because that's even better than branch prediction. Branch prediction, you can be wrong. Doing parallel execution and killing the path that was wrong, faster. It's pretty cool. Like, so we end up using these kinds of tricks to leverage the fact that the performance, the speed in a CPU, the speed inside of a GPU is incredibly high. Very, very fast. So, of course, then we put a little bit of DRAM back in the CPU because we can. Okay, fine. And that helps make the cache bigger. In essence, what we end up with is an extra level of cache. So we replace the last level of cache with an almost last level of cache and put a last level cache in there. Okay, fine. That's the way caches work. Caches work going from fastest to less fast to slower to even slower than that to slowest. And at each layer in a cache hierarchy, what we're doing is squeezing locality out. What we see in multi-layered caches is that by the time we get down to the bottom, what we have is uniform random. And there's nothing we can do to make that faster. We just pay the price. Okay, sorry, you got to go to disk. Uniform random. Okay. But overall, our average performance is way higher because we have lots of locality. Most of the time when your computer is running something, it's running the same little bit of code that it's been running for the last 5 minutes. It's accessing the same data. Yes, it does change over time, but the bulk of it is the same code running over and over again. The operating system pretty much sits in memory entirely. It's crazy when you see people building their operating system pageable. They do it because there's stuff in the operating system that doesn't end up getting used very often. When we go to data center scale, we have thousands of these components. We have lots of general purpose components. We have specialized configurations to handle particular workloads. Farms of GPUs, because we're doing lots of machine learning. I mean, Microsoft is funding OpenAI. Do you know how they're actually funding them? Did you notice that? I wasn't super surprised. It's not like they're shoveling cash over at OpenAI. No, what they're doing is they're giving them lots of CPU and GPU cycles to run their models, which is really what OpenAI needed. So almost all of what Microsoft is providing for them are data center services. There's a lot of work being done in hyperscale computing as well. And that's hyperscale is where everything is just getting bigger and bigger. And exascale is another term that I've heard. People who are starting to worry about storing zettabytes of data, processing, and maintaining the necessary infrastructure, managing that. Large language models are notable because they are really expensive to train. They have huge data sets. They have vast amounts of computational resources that are required. But what's interesting is that now that people have proven that you can actually get someplace with these, other people are coming along and saying, but you know, you can get almost as close with like 1/10 of the resource. And so we see a really cool dynamic tension there. Spending those resources sometimes, even though super expensive, ends up giving us the insights necessary to say, yeah, but it's worth optimizing this case now. How can we make this better? How can we make it? Lots of management challenges and things. I've already mentioned multi-tenancy, where we have to worry about security, but we also have to worry about just the fact that when everybody spins up all at once, things get slow. So I have a load balancing problem. I have to share resources. I have to manage these things. Orchestration of the load across these data centers is complicated, and it's generally bound by service level agreements that say 99.999% of your jobs will complete within some time bound. And if it doesn't, there's a financial penalty for the cloud provider. And what that means is that if you're working for Amazon, I don't know which company your friend's working for, but pretty much all of them have people who are on standby. Pager duty, they call it. Although I don't know anybody uses pagers anymore except doctors. Still do use them. Have you ever seen a pager? Yeah, those are the things that drug dealers use. So when somebody needs to get a hold of them, and doctors. It's hard. Well, actually, there's not much difference, is there? Yeah. Yeah, so these people actually have folks who are on call. If you're working for Amazon on a critical service and you're part of a team, you may very well reach that point where you know you're important because you are on call. And if things break down, and they break down all the time, you'll get called and you will be asked to go and figure out what went wrong and fix it. Lots of papers on this stuff. There are some references, blah, blah, blah. Borg is Google's orchestration system. I'm not going to go into great detail because it's interesting, but you can actually link to the paper there at the bottom. The Google mechanism for doing orchestration, Borg, and of course the Borg reference is deliberate. It wasn't accidental. They're not talking about Anita Borg. They're talking about the Borg, as in you will be assimilated, the Borg. So it's pretty interesting architecture to look at. I'm not going into any more detail on it. Fun stuff, blah, 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 but we're running out of time. Oh, and Borg, of course, has replication in it. Why it's ultimately interesting for us because they actually have their Axos lock manager, Chubby, dealing with the 5 replicas, 5-member replication set that they in Borg with a 10-second failover time. And each replicate contains a cell state of a Paxos-based key value store. See, it's all there under the covers. It's all part of the way that we build modern data centers. I mean, Borg is alive and well, and Google is the smaller of the cloud vendors. You know that means that Amazon and Microsoft also have similar services. They have to. Same problem they all have to solve. Blah, 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 blah. Okay. No, Lego OS was how do you build an operating system with aggregated services? And what they did was they walked through the steps that we've gone through to disaggregate. They pointed out that once you move the TLB and the MMU off the CPU and into the memory itself, it changes the nature of the operating system. So Lego OS was, in fact, proposing themselves as an operating system for these kinds of disaggregated systems, if that makes sense. They're saying we need a new operating system. They're not the only person arguing that we need a new operating system. You've been working with Reto, and Reto, of course, came from Mothy's group, and they were working on Barrelfish for quite a while. And Lego OS does actually give credit to Barrelfish, for instance. Mothy's wandering around giving this whole interesting talk about how Linux, and he specifically picks on Linux here, he says that basically the hardware manufacturers treat Linux like it's a leper at this point. When they build new hardware, what they do is they squeeze Linux into a little tiny isolated environment because it's such a broken piece of shit. And I'm paraphrasing slightly. I think Mothy is actually a little more specific about it, but I don't think he would disagree with my paraphrase at all. And he has some really good points. And he's talking about this as being a challenge in architecture. And it's a challenge for systems because when you take your operating system, isolate it into a little box because it's become broken, well, there's wrong. At data center scale, and Linux is what they run on the actual servers themselves, but many times there are lots of custom components and custom pieces here that have nothing to do with any of the classic operating systems. And so that's why things like Lego OS start to make sense. You run VMware, ESXi, for example. VMware it's a hypervisor. Hypervisors become a complete replacement for what's traditionally been the operating. Same sort of thing. At any rate, let's wrap this up because we're out of time. Nice little walk through data center services, talking about some of the interesting challenges there. Hand wave at Borg. Like I said, not going to be on the final. Just here to try and give you some further understanding that we've just scratched the surface of this world. What do I know about OpenAI? Aside from the fact that it seems to be a goat rodeo? Have you ever been to a rodeo? Well, then it won't make any. In terms of what? So OpenAI is a not-for-profit organization that was built around this idea that the organization should try to protect humanity from artificial intelligence. They wanted to foster an environment where it was more important to protect humanity than it was to promote progress of AI. So they wanted ethical AI. And I don't know if you've seen much about the history of ethical AI, but the history of ethical AI is mostly it gets slaughtered by the people who want to make more money. When Google had a really cool group of people who did ethical AI work, they all got fired. And it's a very interesting problem. Of course, then today I just saw an article for class that said that we have more to worry about rogue viruses than rogue AIs at this point. That's a little disturbing, isn't it? I think that the brouhaha with OpenAI this last indicates that there is a very interesting tension, that's a nice polite term, between the balance of people who care about humanity and people who care about money. I actually think there are a group of people who would prefer to have money than humanity. I mean, I won't point any fingers or name any names, Elon Musk, but you know, get the idea. Is there a specific vendor? Most of them are using NVIDIA. NVIDIA is by far the runaway, except in China where they're using their own homegrown now, since NVIDIA doesn't sell them chips now. Well, they sold them one. You got the joke finally. That was always the joke about, right? You know, you sell something to China, you sell one. Not entirely true, but not entirely untrue. Some people have a flexible definition of intellectual property right. What's mine is mine, and what's yours is mine. Getting married. All right, any other questions? Cool, well, so then I'll see you on Tuesday, and that will be the last actual lecture, and then Thursday I will do a final review session. Then the following Tuesday there will not be a lecture or code for the capstone. Is decided that I would rather have you working on that than sitting here not coming to class and not thinking about your code, or sitting here in class and worrying about your code, because everybody's worrying about the code for some reason. Then the alternative optional, you don't have to show up for it. No pressure there. Final on Thursday the 7th at 5 o'clock. And then on Friday, December 22nd at 7 p.m. in whatever godforsaken place they put us, we'll actually have the real final. Right? This is a show of hands. How many of you plan on taking both finals? How many of you plan on taking neither final? How many of you plan on only taking one of the two? A lot of more people are saying they're going to take both of them. You're really hedging this thing. Maybe I should have said I'll take the lowest of the two. Too late now, I can't change it. All right. Have a good night.